Welcome to the Deep Dive. We're your guide to, well, cutting through the noise in tech. Today, we're taking a really fascinating journey into DevOps tools for Java developers. Our mission really is to distill the essential practices, maybe some surprising insights too, that turn raw code into, solid production-ready applications. We want to help you become incredibly well-informed without getting bogged down in all the jargon. And guiding us is a really comprehensive source from industry veterans, Stephen Chin, Melissa McKay, Ixchel Ruiz, and Baruch Setagursky.
Yeah, what's really compelling about this guide, I think, is how these authors, and they're deeply embedded in the industry, they don't just list tools, not at all. They actually unpack the entire life cycle, from that very first line of code all the way to continuous operations. They managed to make some genuinely complex topics pretty accessible, drawing on decades of real-world experience. It's quite something.
Okay, let's dive right in then. What really surprised me right off the bat was the origin story of DevOps itself. Our source highlights this idea that DevOps is an entirely invented concept. Okay, fair enough. But here's the kicker. The inventors came from the ops side of the equation.
Right, from operations.
Exactly. Think about that. And, foundational narratives like the Phoenix Project, which is really more of a novel about a struggling IT department, not some dry technical manual.
Mm-hmm.
They powerfully underscore this ops-centric beginning. Yeah. And this origin story, it fundamentally reshaped what done even means for a developer.
It really did.
It's not just about writing code that works anymore. It's about making sure that code is, simple, readable, understandable, and easy to deploy. Plus, all the non-functional requirements satisfied, tests passing the works.
And the key point the authors make is that a truly well-done job can never adequately be measured or even known without the involvement of and clear communications with ops personnel.
That's a massive mental shift, isn't it?
It absolutely is. And building on that, what's equally striking is how this mirrors the world's changed definition of quality. I mean, think about banking. Maybe 10 years ago, a 12-hour website downtime for maintenance. That was just normal. Expected, even.
Yeah, you just planned around it.
Right. Today, completely unthinkable. You expect your bank to be always on, always available.
Always.
And that fierce urgency, that demand for constant availability, that's what truly drives DevOps. It's not just a buzzword. It delivers tangible benefits. Better quality, real cost savings, faster feature deployment, and critically stronger security.
So it's about business survival, really.
Absolutely. Survival and growth.
Yeah.
And this environment, it thrives on what are often called T-shaped people.
T-shaped.
Yeah, individuals with deep expertise in one specific area, but also a broad understanding across many others. They're perfect for bridging that dev and ops gap.
Yeah.
Some even talk about your-shaped individuals, especially in Russian tech circles, implying deep expertise in multiple areas, plus that broad base.
Okay, that makes a lot of sense. So this focus on quality collaboration, it naturally leads us to how we manage the code itself, right? The foundation.
Source code management, SCM.
And SCM plays several vital roles, doesn't it?
Oh, definitely. Collaboration, obviously. Managing different versions, keeping that crucial history, attributing changes, knowing who did what when, handling dependencies, and ensuring quality through things like peer review.
The history is pretty interesting, too, the evolution through generations.
Yeah, it's come a long way. Started with file locking systems like SCCS, RCS, ancient history now, almost.
Feels like it.
Then came centralized systems, Subversion being the big one for a long time.
SVN, yeah, I remember that well.
And now we're firmly in the era of the third generation. Distributed Version Control Systems, DVCS.
And Git is just dominant.
Completely. The numbers are staggering. That JetBrains State of the Developer Ecosystem 2020 report found Git-based systems account for over 96% of the commercial source control market. It's just everywhere.
Wow. And the guide even suggests a practical exercise, right? The first pull request on GitHub.
Yeah, which is a fantastic hands-on way to quickly grasp how distributed version control works, how easy contributing can be.
Makes it less intimidating.
Totally. And for developers getting started or even experienced ones, those core Git commands are your daily toolkit. Things like add to stage changes, commit to save them locally, push to share them.
And merge or rebase to integrate work from others.
Exactly. Your bread and butter.
Okay, so moving on. What genuinely surprised me in this deep dive was learning just how deep the history of containers actually is.
Right. It feels like such a modern thing.
Totally. But the source reminds us of Melissa McKay's great analogy, the elephant in the room. It's crucial to actually ask, what is a container and why would we even use one? Before just diving in.
Good point. Don't just follow the hype.
And the history, it goes way back. Crute in Unix in 1979.
Wow, 79.
Yeah. Then FreeBSD jail, Google's SU groups, Linux containers LXC, all this groundwork.
Laying the foundation.
Exactly. Paving the way for Docker in 2013, which really blew the doors open on popularizing the concept.
Docker really was the catalyst.
And then Kubernetes following in 2015 to manage it all at scale.
The orchestration piece.
So why are they so widely adopted now? The source calls them a lightweight solution that promises to solve most of the issues around application consistency, process isolation, and OS-level dependencies.
And that consistency is huge for development and testing.
Oh, definitely. The guide says containers help keep the runtime environment consistent, greatly reduced, since the environment is shipped along with your application. Think about onboarding new developers so much easier.
Right. No more works on my machine problems.
Exactly. And reproducing bugs becomes way more reliable across different setups. It's a game changer.
And this really forces a different way of thinking for developers. The key insight here is why this isn't just an ops problem anymore. It's very much a developer's concern now.
How so?
Well, packaging your application into a container, it requires more thought, more foresight from the developer than you might initially think. It effectively pushes that DevOps mindset left, right into the development phase.
Shifting left, yeah.
Exactly. And when we talk container anatomy, you've got the Docker file that's your blueprint, then the Docker architecture. The CLI you interact with, the background daemon doing the work, the registry where images are stored, and the underlying runtimes like runc or container that actually run the containers.
Okay, and maybe we should quickly clarify that Kubernetes deprecation.
Oh yeah, good point. The Kubernetes deprecation of the Docker container runtime in version 1.20,
Right.
it caused a bit of panic.
Right.
But it doesn't mean Docker itself is dead or gone from Kubernetes, not at all.
Right.
It just means Kubernetes changed the way it talks to Docker's internals. It stopped using a thing called Docker shim because Docker itself now uses container underneath anyway. So Kubernetes just talks directly to container or other compatible runtimes. It's more of an internal plumbing change.
Got it. So Docker is still very much relevant.
Absolutely.
Yeah.
Now, thinking about those images, image layers are like stacked changes, right? Deltas. Each layer builds on the previous one, and each gets its own unique digital fingerprint, SHA-256 hash.
And using the layer cache makes builds faster.
Hugely faster, usually. But you have to watch out for the caveats, like failed cache. Sometimes you don't want the cached version.
Right, if an underlying dependency changed but the command didn't.
Exactly. And the source offers some great best image build practices and container gotchas. Simple things, but crucial. Respect the Docker build context. Use a Docker door file to keep things lean. Always use trusted base images. Keep your final images small. And please, please protect your secrets. Don't bake credentials into the image.
Absolutely critical. Okay, so that's packaging. Let's shift gears slightly from how we package to how we structure the applications themselves, which brings us to microservices.
Yes. Microservices.
Defined in the source as deconstructing ideas and concepts into simple or composite parts, leading to this finer granularity.
Sounds elegant on paper, doesn't it?
It does. But it also introduces, and the source is clear on this, significant complexity.
Oh, yeah. Suddenly you might be managing thousands of microservices running asynchronously.
Wow, thousands.
And that leads to real challenges, like how do you track a request across 10 different services? Distributed logging and tracing become essential, but hard.
That's where things like API gateways come in.
Exactly. They act as a single front door. Clients talk to the gateway, and the gateway figures out which microservice or services need to handle the request. It simplifies the client side.
Makes sense. And for Java developers, the source compares some popular frameworks.
It does. Spring Boot, Micronaut, Quarkus, Helidon, the main contenders. It notes Quarkus often offers the fastest startup and smallest executable size, especially when compiled natively with GrailVM.
Which is a big deal for cloud costs and performance.
Huge deal. And this idea of breaking things down, it sort of culminates in serverless or function as a service.
Taking granularity even further.
Right down to the smallest reusable piece of code. Often just a single function or method that runs on demand.
Fascinating evolution. Okay, so we have our code managed well. We have our applications packaged in containers, maybe structured as microservices. How do we make sure everything actually works together seamlessly and consistently?
That's the domain of continuous integration. CI, an absolute cornerstone.
And the source reminds us its roots go back to Kent Beck's extreme programming.
Yep, XP. Initially, CI was pretty basic. Sometimes just about getting a project to build it all after development was complete. like who even compile this thing.
Just getting it to build was a win.
Right. But today, the goal is much more proactive. It's about identifying bugs and compatibility issues as quickly as possible through very frequent automated builds.
And Martin Fowler's quote really nails it, doesn't it?
Oh yeah. Continuous integration doesn't get rid of bugs, but it does make them dramatically easier to find and remove.
It's about the when and the how, easily.
Exactly. The key outcomes you want from CI are things like code integration being regular and rarely complicated.
No more integration hell at the end of a project.
Hopefully not. And when bugs are introduced and caught by the CI system, they get fixed immediately. Right away.
The guide even mentions the old practice of having a loud siren go off for a broken build.
Huh. Yeah, the physical feedback loop. Maybe a bit extreme now, but it shows the urgency.
So how do we define these builds? The build scripting tools have evolved too.
They certainly have. From Apache Ant's XML-based approach, which could get pretty verbose, to Apache Maven, which brought in convention over configuration. A huge step forward. It assumes sensible defaults, so you write less boilerplate.
Made things much cleaner.
Definitely. And then Gradle came along, offering even more flexibility with its Groovy or Kotlin domain-specific languages, its DSLs. Very powerful, especially for complex Android builds.
And underpinning all of this is automated testing, right? The safety net.
Absolutely essential. Automated tests are the safety belt for your pipeline. They prevent issues from slipping through to later stages, or worse, to production.
Okay, so building on that, it's not just about building the code anymore, is it? We need to manage all the pieces, the dependencies, and ensure they're secure.
Precisely. As W. Edwards Deming famously said, "In God we trust, all others bring data."
Love that quote.
Me too. And in this context, metadata is that crucial data. We need to capture everything about a build timestamps, the JDK version used, OS info, the exact git commit hash. Tools like Maven and Gradle are great at capturing this.
Why is that metadata so important?
For traceability, reproducibility, debugging, and security. It ties back to containers, too. The source makes a key point. Simply locking down your image versions isn't sufficient from the context of security. Use only trusted base images when building your containers. You need to know what's in those base images.
Which leads us directly into DevSecOps, right? Integrating security throughout.
Exactly. Because the impact of getting security wrong could be catastrophic. Think about supply chain attacks, like the SolarWinds breach.
A huge wake-up call.
Massive. It showed that it's not enough just to secure your own code. You have to trust, but verify, your entire software supply chain, all those third-party libraries and base images.
And the source introduces the role of site reliability engineers here, SREs.
Yeah, a really interesting role. An SRE's job is to balance the push for new features with the need for system robustness and reliability. They often dedicate up to a maximum of 50% of their working time to focus on the operations tasks and responsibilities, keeping the lights on, essentially, while also improving things.
A crucial balancing act. Now, when it comes to security testing, there are different flavors, aren't there? DAS.
Right, several different approaches, and they're often complementary. You've got SaaS static application security testing that looks at your code from the inside out without running it. Great for catching things early in the dev cycle.
Like a spell checker for security bugs?
Sort of, yeah. Then there's DAS dynamic application security testing. This tests the running application from the outside in, mimicking how a hacker might attack it, finds runtime vulnerabilities.
Okay.
IAST interactive application security testing tries to combine the best of both. It uses agents or instrumentation to analyze the application while it's running, seeing how data flows.
Getting deeper insights.
Exactly. And finally, RASP runtime application self-protection. This is less about testing and more about active defense. It tries to detect and block attacks as they happen in production.
But that can have performance implications.
It can, yeah. It's doing extra work at runtime. The source is clear, though. These approaches are not mutually exclusive. On the contrary, they complement each other perfectly.
So you might use several.
Ideally, yes. They recommend starting with SaaS because it finds potentially big threats early with, relatively speaking, minimal effort.
Good starting point. And how do we score these vulnerabilities? CVSS.
Yeah, the Common Vulnerability Scoring System. CVSS gives you a standardized number, 0 to 10, indicating severity. It considers base metrics, temporal factors, even environmental context.
Useful for prioritization.
Definitely. Now, the core idea tying this together is shift security left.
We mentioned shifting left earlier with containers. Same idea here.
Same fundamental principle. Embed security practices much, much earlier in the development lifecycle. Don't wait until the end. And the guide makes another crucial distinction. Not all clean code is secure code.
Ah, interesting. Explain that.
Well, clean code is readable, maintainable, easy to understand. That's great. But secure code also needs to specifically address potential vulnerabilities, follow security best practices, meet compliance rules. They overlap, but they're not identical.
Got it. So how do we evaluate code reviews?
Regular code reviews are key, yes. And the source suggests some creative methods too, like the OWASP cornucopia card game.
A card game for security.
Yeah. It's a gamified way for teams to think about potential threats and identify those evil user stories. How could someone misuse this feature? It builds awareness in a fun way.
I like that. Okay, fantastic overview of building and securing. So now our binaries are built, tested, secured. They're ready. How do we actually get them deployed to our users reliably and ideally without any downtime?
This is where orchestration frameworks like Kubernetes really shine.
And there are Java-specific tools to help build and push the container images?
Yeah, tools like Jib from Google and Eclipse JCube. They integrate nicely into Maven or Gradle builds, making it easier for Java devs to create container images without needing deep Docker expertise.
Streamlining the process.
Exactly.
Yeah.
Now, for the actual deployment strategies within Kubernetes, you've got several options, each with pros and cons.
Okay, let's run through them.
The simplest is probably recreate. Stop the old version, start the new one.
But that means downtime.
Yep. Unavoidable downtime. Okay, for some non-critical things, maybe, but usually not ideal. Then there's rolling update. This is often the default. Kubernetes slowly replaces old pods instances with new ones, one by one or in batches.
So no downtime.
Generally no downtime, but the rollout can be slow, and you temporarily have mixed versions running.
Okay, what else?
Blue-green deployment. Here, you deploy the entire new version, green, alongside the old version, blue. Once green is tested and ready, you switch all the traffic instantly from blue to green.
Sounds good. Fast rollback too, right? Just switch back to blue.
Exactly. Quick, low-risk rollbacks. The downside is you need roughly double the resources during the deployment.
Trade-offs.
Always. And finally, there's canary deployment. This is
Yeah.
more sophisticated. You release the new version to a small subset of users, first the canaries, like 1% or 5% of traffic.
Right.
You monitor closely. If everything looks good, you gradually increase the traffic to the new version, maybe using service mesh tools like Istio for fine-grained traffic weighting.
Very controlled rollout.
Very controlled, minimizes risk exposure.
Okay, so beyond just getting the new version out, Kubernetes helps manage the running application too. Health checks.
Absolutely critical. Liveness probes check if your application is still running. Readiness probes check if it's ready to accept traffic. Kubernetes uses these to know if it needs to restart a container or stop sending requests to it.
And resource management. CPU, memory.
Yep, you define requests, what you think you'll need, and limits the maximum allowed. This helps Kubernetes schedule pods efficiently and prevent noisy neighbors.
And persistent data. That's always tricky with containers.
It is. Kubernetes offers ways to manage persistent volumes, connecting containers to storage that outlives the container itself. Still requires careful planning, though.
And how do we know what's going on inside these distributed systems? Observability.
Crucial. It goes beyond just monitoring. It's about monitoring, logging, and tracing. Understanding the internal state from external outputs. The RED method is a popular framework for metrics. Rate, requests per second, errors, number of failed requests, and duration, how long requests take.
Gives you a good snapshot of health.
Definitely. And if things get busy, horizontal pod autoscaling, HPA, can automatically scale the number of pods up or down based on metrics like CPU usage.
Automatic scaling. Nice.
Very handy.
So this brings us to a really critical point you touched on earlier. Why is all this, the continuous uptime, the continuous updates, why is it so fiercely urgent for businesses today?
It really is urgent. The contrast with how software used to be delivered is just stark. Think back to, say, Nokia phones in the early 2000s. If you needed a software update, you often had to physically go to a service center.
Oh, man, I remember that.
Right. Compare that to your Apple iPhone today. One click, over-the-air update, maybe takes a few minutes while you sleep, or apps updating automatically from the App Store.
Worlds apart.
Completely different expectation, and the cost of not updating or getting updates wrong can be astronomical.
You mentioned Equifax earlier.
Equifax, in 2017, a textbook example. They failed to patch a known vulnerability in Apache Struts, a common Java web framework. The cost. The source quotes $1.4 billion on cleanup costs and an additional $1.38 billion to resolve consumer claims. Billions from one missed update.
Unbelievable.
Then there's the Knight Capital Group story from 2012, a financial firm. They were doing a deployment, and a manual error meant the new code was deployed to only 7 of their 8 servers. The 8th server was left running old, conflicting code.
Sure.
Because their trading was highly automated, this inconsistency triggered chaos. They lost $468 million in just 45 minutes, a continuous update disaster waiting to happen due to manual error.
45 minutes, wow.
Even the big players aren't immune if they slip up. Cloudflare, who basically run a huge chunk of the internet's infrastructure. They've had several major outages traced back to deployment issues. A bad router rule in 2013, a faulty regex pattern in 2019 that spiked CPU usage globally, a software bug during a rollout in 2020. These incidents show how bypassing best practices like progressive delivery, like Canary, and proper observability can have massive global consequences.
So the stakes are incredibly high.
Incredibly high. Now, for Java specifically, there's been a challenge with the faster 6-month release cadence introduced after Java 8.
Adoption hasn't been great, has it?
It's been poor, frankly, beyond Java 8 for many organizations. Partly because the perceived value wasn't always immediately obvious for the upgrade effort, and partly because Java 9 introduced significant disruptive changes with the module system, Project Jigsaw. It made updating feel like a much bigger task.
Created inertia.
Exactly. And thinking beyond servers. In the mobile world, particularly Android, device fragmentation is a huge challenge. You need continuous testing across hundreds, maybe thousands of different devices with different screen sizes, OS versions, hardware. Ensuring your app update works everywhere is a massive undertaking.
A complex testing matrix.
Extremely complex. So pulling it all together, the source summarizes the continuous update best practices you need to aim for. Frequent updates, ideally automatic updates, comprehensive automated testing, progressive delivery strategies like Canary or Blue-Green, robust observability, state awareness during updates, and crucially, the ability to perform quick local rollbacks if things go wrong.
Okay, so let's try and wrap this up. What does this all mean for you, the listener? We've really covered a lot of ground. From the surprising ops-side origins of DevOps itself, through managing source code effectively, harnessing the power of containers and microservices, then the rigor of CI, adding that absolutely critical layer of security with DevSecOps, all the way to deploying reliably with Kubernetes strategies and understanding the huge real-world impact of continuous updates.
It's been quite a journey.
It has, and hopefully you now have a deep dive packed with those essential nuggets, those surprising facts that really arm you to be truly well-informed about DevOps, especially in the Java world.
And maybe a final thought to leave you with. This continuous evolution in software means done isn't really a fixed state anymore, is it? It's become this dynamic, ever-improving process. So how does embracing that continuous journey, that constant improvement, how does that change your own definition of success when you're building and delivering software? What stood out most to you from this deep dive? And maybe where will you choose to dig deeper next?